Ever notice like those stacks of paper cups at a coffee shop?
Ah.
All identical. Or even like perfectly laid tiles.
It's like the universe is saying, these two things, exact copies, just different spots. And that is congruence.
So we're talking congruence, but specifically with triangles, right? You've been digging into that geometry textbook.
Chapter 7, Congruence of Triangles. Yeah.
Yeah.
Let's unlock some secrets.
Okay, so same shape, same size, that's the basic idea. But this chapter gets into like how we know for sure if two triangles are a perfect match.
It's more than just eyeballing it. We need ways to be certain about congruence. And the chapter gives us the tools, starts with the building blocks. Lines and angles.
Makes sense. Before we tackle triangles, we've got to be on the same page about what makes their parts congruent.
Right, like you can't build a skyscraper without understanding beams and rivets, right?
Sure.
So the book uses this trace copy idea. Like, imagine putting one shape on top of another. Perfect match. Boom, congruent.
Ah, okay. And they give the example with line segments. One covers the other perfectly, same length, they're congruent. If one's even a tiny bit longer, no way to make them fit.
Exactly. Same length is key for congruent line segments. With angles, it's about their measure, that degree opening. But things get even more interesting with triangles.
Triangles?
Yeah.
They seem simple, but 3 sides and angles to think about, right?
You got it. And it's not enough for sides or angles to just match up randomly. It's about how they relate within the whole triangle. That's where these criteria come in. SSS, SSSS are congruence detectives.
Love that. And the chapter uses that fun game with Apu and Tipu to introduce them.
Right.
Trying to outsmart each other with triangles.
Makes it stick. So their first challenge, the SSS criterion, stands for side, side, side.
Okay, so it must be all about the sides of the triangle.
Exactly. And their game shows knowing just one side length isn't enough for congruence.
Yeah.
You could have a short, stubby triangle and a long, thin one, both with a side that's 5 centimeters.
Right. Wouldn't guarantee they're identical.
And what they figure out is you need all 3 sides of one triangle to match the corresponding sides of the other in length. Then, boom, congruent triangles. No matter how you rotate or flip them.
The trace copy thing, but with all sides. Line them up perfectly, triangles are a match. I'm starting to get this detective thing. But there's more than just sides, right?
You're one step ahead. Next level, SAS criterion. This is where sides and angles come in.
SAS, side, angle, side, right.
Yeah.
But does any angle work? Or
There's a catch. It's not just any angle. Apu and Tipo's game shows this. It's got to be the angle right between those 2 sides, the included angle.
included angle. So like it's sandwiched between the 2 sides we know are congruent.
Exactly. And the book gives those examples where they try to trick each other, right? Just 2 sides or a side and a random angle, not enough. It's all about that angle's placement.
So SAS only works if the angle is right there between the matching sides, like the key to the congruence puzzle.
And speaking of keys, ever notice how they work? The groove's got to line up perfectly with the lock. If SAS is similar, the sides and included angle, they're like those grooves. Got a line for the triangles to be congruent.
Wow, that's a good way to think about it. Okay, so SSS, SSS. What's next in our congruence toolkit?
Ready for ASA, angle, side angle. Apu and Tipu, they're trying to figure out if knowing 2 angles is enough this time.
2 angles. Like, picture those tiled floors again. Tile corners are right angles, so at least 2 angles match. But tiles can be different sizes, right?
Exactly. And that goes back to the whole 180 degrees in a triangle thing. You know 2 angles, you know the third. But like you said, doesn't mean the triangles are the same size, just the same shape.
So just knowing 2 angles, not enough for congruence.
You got it. With ASA, we need those 2 angles, but also the side connecting them, the included side, that's got to be congruent too.
The angle-side-angle combo, something like beams in a roof, maybe.
Yeah.
They'd need to be at specific angles to hold the weight and the right length, too.
Perfect example. Those beams need that exact ASA setup to be safe and sturdy. And speaking of sturdy, our last criterion takes us to right triangles.
Right triangles. They always feel simpler, since one angle's automatically 90 degrees.
And that simplicity carries over to the RHS criterion, right angle hypotenuse side.
RHS. Sounds a bit intimidating. But we're dealing with right triangles, so hopefully not too bad. What's special about RHS?
Remember that thought experiment from the book? About drawing a right triangle. If you only know one side length, you could draw tons of different sized right triangles. And knowing one other angle besides the right angle doesn't help much either. But if you know the hypotenuse, that longest side, and one of the other sides.
Wait, I think I see where you're going with this. With the hypotenuse on one side, we've locked in both the size A and D shape. There's only one way to draw that.
Exactly. That's the elegance of RHS. Hypotenuse and one side of a right triangle match another. They're congruent.
Like having two puzzle pieces that fit perfectly tells us the whole picture has to be the same. We've come a long way from basic shapes to all these criteria, SSS, SS, ASA, now RHS. But I feel like this congruence idea goes way beyond just triangles, right?
Absolutely. It's like we've leveled up. Now we can see those principles everywhere.
So if it's not just triangles, where else does congruence pop up?
Well, remember those square tiles? What makes a square a square?
Four sides, but they all have to be equal, right? And those corners are always right angles.
Exactly. So congruent squares, we're looking for all sides matching up perfectly.
Like those rows of windows on a skyscraper, they have to be congruent or it'd look kind of crazy.
And that enrichment activity section got me thinking about circles. They only have that one measurement, their radius.
So two circles, same radius, that's our congruence clue.
Exactly. It's like using a compass. Every point on the circle is that same distance from the center, the radius. Change the radius. You change the whole circle.
This deep dive has been eye-opening. But beyond text brace, why does congruence matter so much?
It's more relevant than you might think. Imagine a world without it. Your car engine wouldn't work. Pistons, cylinders, gotta be perfectly sized. Manufacturing relies on it, from tiny screws to huge airplane wings.
So that's why my furniture sometimes actually fits together, congruent parts.
Yeah.
And I'm guessing bridges wouldn't be too safe without it either.
Exactly. Congruence means stability, things working reliably. It's like the hidden force behind good design in our world. And what's cool is, even though we've been talking about shapes being exactly the same, congruence helps us understand transformations too.
Transformations, like funhouse mirrors warping your reflection.
Not quite. I'm talking about slides, flips, turns in geometry. Even if we do those to a triangle, as long as the sides and angles keep their relationships, the triangles are still congruent.
So no matter how you move it around, slide, flip, turn, if the measurements are the same, it's fundamentally the same shape. Mind-blowing.
It is, and that leads to even more possibilities in geometry. Like, we didn't even touch similar triangles. Same shape, but different sizes. Another deep dive for another day.
You've given me a lot to think about with all this congruence. So simple, but such a big deal.
It's all about those underlying patterns. And once you start looking, you see congruence everywhere. Nature, the things we build. It's fascinating.
So listeners, next time you notice the symmetry in nature or things fitting together perfectly, remember, congruence. It's more than meets the eye.
And this is just the beginning of the geometric adventures out there.